Actually, Dario give very nice introduction to the point contact spectroscopy in all the aspects, especially to the spectroscopy of superconducting of the contacts between superconductor and normal metals. In my talk, I just wanna give you results which we measured for the iron selenide, and in particular we conducted some measurement at sub-Kelvin temperature to actually distinguish certain things which we couldn't see at higher temperatures. This work was done in collaboration with Center of Low Temperature Physics of Slovak Academy of Science as a part of a joint project between Ukrainian and Slovak Academy of Sciences. I actually skipped this part because Dario already told how the contact spectroscopy works. I only focus on one thing, that if the Dario usually looks on differential conductivity, we look on differential resistance, which means that our spectra is just turned upside down. That's what you have to take into account. Here I want to present some results on soft contact spectroscopy on iron selenide, which we measured earlier. Here's the temperature dependencies and magnetic field dependencies. For the point contact spectra, we see very nice gap features. But when we trying to fit it with one gap, we couldn't succeed actually get a nice results. So in 2017 we tried two approaches. One is to use one anisotropic gap, and another to use two gap approaches with parameters which we're using for the fitting is in case of two gaps, it's a presence of weight factor, which actually included say how much presence of one gap dominate over another. Also, there was a barrier. To simplify our model, we assumed that smearing parameters are the same for the both gaps, and also we had the scaling factor, which says how much we have to stretch or extract our calculated spectra to actually match with with experimental data. The same parameters we had also for the anisotropic gap, with the difference that we had another parameter instead of weight factor. We had anisotropy parameter factor, which says how much our gap changes in space. If you look closer to how our fit matched to our experimental data, it became obvious that it is slightly better. Just we look on these small things, slightly better works for the anisotropic gap. But then when we start to fit it with the temperature, we find out that alpha parameters start to grow with the temperature, and then by approaching to the critical temperature, we've seen that it changes from 0.3 up to 1, which is physically unreasonable. It means that by rising the temperature, we increase the anisotropy of our gap. So we did assume that indeed we should actually stop on the idea of two gaps being present in this material. Indeed. Later on that year, it was shown also with Cunnington ion spectroscopy, where they utilized Bogolubov quasi-particles interference, that indeed there is two gaps observed in this material, one present for the whole pocket of Fermi surface, another for the electron pocket of Fermi surface, which correspond also red to the red, blue to the blue. And both of them are quite anisotropic. Alright, so the next year another article appears with angular resolve photoelectron spectroscopy. Also was shown the same results. There is a high anisotropic gap present to the electron pockets, and also highly anisotropic gap is present for the whole surface. a whole part of the thermal surface. We couldn't recognize that in our previous measurements, so what we decided to do, we know from from beginning of point contact spectroscopy that there is such thing as the energy resolution for the spectra, and the energy resolution depends on the temperature and on modulation signal. If we exclude the modulation signal actually and try to look at temperatures, lowest temperature we've been using before, like 3 Kelvin, that energy resolution is like 1 milli-electron volts. But when we go to the lower temperature and we go sub-Kelvin region, our energy resolution improves 10 times. So what we done, we actually find the place where we can take our sample, glue the contacts to it, and cool it down to the temperature we desire. And actually we did get few contacts with nice Andreev spectra. We choose the best one, and we start to fit our data with the theoretical approaches. So we then we use 3 of those approaches. It's single anisotropic. Sorry if it's not really visible now on the screen. So in the middle we have single gap. On the bottom we have single anisotropic gap. On the bottom we have 2 gaps which isotropic, and on the top we have 2 gaps which is anisotropic. And straight away the middle spectra shows that whatever we tried, how to try, how different we change the fitting parameters, we couldn't get very nice match between the calculated and measured data. And for simple 2-gap isotropic model, we managed to get very nice correspondence between the calculated and measured data. The same also, even that we got plenty of fitting parameters, but it also we was able to get the nice correspondence between the calculated data and measured data. The only difference between this top and bottom fits are that the scaling factor on the top case we had close to 1, but for the lower case we have it pretty big, so it means that we had to stretch a lot our calculated our theoretical data to match experiments. From that we conclude the more likely, and actually it was shown already previously with ARPAS and STS, that in ferrum selenide we have 2 gaps which is highly anisotropic. Here I just want to show you how hard it was actually to do this matching, because at low temperature we still have some discrepancies which we can manage to go around, but as soon as we start to heat up the samples to 5-6 Kelvin, the discrepancy and ability to choose the parameters became so high that then further we cannot match our data with I mean, like, the variation is really huge, so there is no really point to look further, because we cannot get some exact and precise data out of our spectra. With this, actually, I want to summarize the talk and say that we managed to get nice Andreev spectra at sub-Kelvin temperature, which shows that it is possible to fit it only with within the 2-gap models. More likely, it is anisotropic, which corresponds to 2 anisotropic gaps, which very nicely correspond to STS data and ARPAS data. And what is most important to this talk, that we show that sub-Kelvin temperature are crucial to a certain details of superconducting gap structure, especially for the multi-band materials when Andreev reflection spectroscopy is applied. With this, I want to thank you for your attention, and I want to thank also Dmytro for providing the samples, Oksana Kvitnitskaya for helping with this work, and Institute of Experimental Physics for their hospitality.
I actually have one. You mentioned this scaling factor. Sorry, I did not understand exactly what. So this is vertical.
How much vertically we have to shift. We have to shift our. Stretch. Our theoretical curve to match it with experimental. Ideally,
because you do not use any broadening. Or
we use a broadening. Okay. First broadening comes from a temperature, and another broadening comes from gamma, which is which actually includes.
And still you need this scaling factor to adjust things.
We did need.
But physically, what could this mean?
It can mean simply that, for example, we have some parasitic signal which actually shifts slightly.
Don't tell anyone, but in some compounds we also have the same problem. Not these ones I showed. So I'm curious to know what is your opinion.
Because sometimes when you run the experiments, you not exactly can match the phase, right? So sometimes it can be some shift, some shift of your signal. Sometimes there is some parasitic signal which goes through your filter, still goes through your filter. So which has to, and then you have to adjust it.
Okay, thank you.
Thank you very much for the concept.